Hey guys, what's up? Hopefully you're having a good week so far, a good start to your week. Um, Monday is here, about 4 weeks in for us. We are cooking. Hopefully we can get this done before we have to cut off our quiz today. So we're going to talk about some tensor notation for matrices and linear algebra basically today. So I just want to kind of just really try to hammer home what these indices represent and try to get that in place before we get into what tensors actually are next time. Hopefully that'll make a little more sense after we get through today. So what's up with the indices? So what's up with the indices? So I've written this thing like quite a few times, aij. Well, the idea is if you have an index up and an index down, let me say this. So what's up with the indices? Something like this. The answer, the number of indices tells us what the dimension of the array is. For example, if it's like ci up, it's a one-dimensional array. So 1D array. We can say like a vector. Or if it's like bj down, then it's a 1D array. Again, like a vector. That's like one index. If you have two indices, like aij down, that's a 2D array, like a matrix. If you have ai up, j down, again, that's a 2D array, again, like a matrix. If you had 2 up, like aij up, 2D array, again, like a matrix, just like a matrix. Now, next time we're going to find out when do they go up and when do they go down, but all that's important is to know that the things, the objects, the arrays that have two indices are represented by matrices. If it has a one index, it's represented by like a vector notation. It has just a single like row of components or a single column of components. It doesn't matter how you represent it necessarily for a single index. But if you have two indices, like we have down here, so all of these have two indices right here. If you have two indices, then you're basically representing it with a matrix. So we know aij down, we have the row index and the column index. And that's very familiar from working with matrices, what we did with matrices and everything. That's kind of how it's all introduced. So if you have aij, so I up, j down, the upper index goes through your rows, so row index, and the bottom one would be your column index. So basically it's like left to right, top to bottom. And then aij up, again that would be, the first one is row index, and then column index. So the first one you see is the row index, the second one you see is a column index if you have two indices. So the array, the 2D array, would be a matrix no matter where the indices are. So consider the following matrices. You could have something like A11, A12, A21, A22, and that's a 2 by 2 matrix. You could also have A11, A12, A21, A22. That would be another 2 by 2 matrix. You're just using the indices in a different location for some reason. We don't know what that reason is, but once we get there, it'll make a little bit more sense. So, and then lastly, we could have something like A11 up, A12 up, A21 up, A22 up. And so all three of these would be a matrix, but we just use a different index notation depending on certain properties of that matrix or certain properties of the functions in that matrix. So in general, kind of like vector fields, these things that we call tensors will be just arrays of functions. So this is not the definition, but just a preview. So preview. Tensors are arrays of functions. Basically, if it has one index, if one index, then the tensor is a vector field. Now, vector fields can have different types of properties, which we'll see when we get to chapter 3, and that will determine whether that vector field, the index will go up on its components or down on its components, depending on some properties of that vector field. So that's more or less the idea for today, is really just to kind of represent matrices and vectors using indices either up or down. And now we kind of get a little bit better idea of like what's going on with the notation, not completely understanding why it's up or down, but at least knowing, okay, what's represented if I have like two indices. Well, it's basically a matrix, matrix of functions. Now, let's see. Example. Let's multiply these two matrices given that they have the following representation. So let's multiply. So I have A11, A12, A13, A21, A22, A23. And multiply that by the matrix B11, B21, B31, B12, B22, B32. Well, what's the size of the resulting matrix going to be? Well, this is a 2 by 2, and this is a 2 by 3. This is a 3 by 2. So the resulting matrix is going to be a 2 by 2 matrix. And its components, we'll call it, we'll call them C11, C12, C21, C22. Again, you don't know at this point that there should be one up and one down. Once we get through chapter 3, we'll understand completely. But for now, we'll just write it like that. And what would the C11 component be? So the solution would be C11 be equal to the first row of A, so call this matrix A and this matrix B, the first row of A dotted with the first column of B. So that would be A11 times B11 plus A12 times B21 plus A13 B3, 1, which is actually a summation over the lower index on A and the upper index on B. So I could write this as A1I, BI1. So C11 would be represented by A1I, BI1. And then C12 would be the first row of A dotted with the second column of B, so that'd be A11, B12, plus A12, B22, plus A13, B32. Again, that's a Einstein summation, so that's A1I, BI2. And you might see a little bit of a pattern here that this one matches this one right here, and this one down here is going to match this one down here. This one matches this one. This 2 matches this 2. And the summation is always happening between these two components right here. So what we could say in general is that Cij, well actually let me say Cjk in general, Cjk would be Aj, Bik. So that would be the general way to write the matrix multiplication. So general form of this matrix multiplication. Now all I would have to do is plug in values of j and k, sum over I, and I get any value in my matrix C. And note this is much more general than just a 2 by 2 matrix. So this notation, this expression is not limited to our example matrices. The expression is the general notation for matrix multiplication. The only thing we're excluding now is the summation sign over I. So basically what we had before was that Cjk would be the sum I equals 1 to n Aj Bik. So the only thing is we're not writing that summation symbol because we're using the Einstein summation convention. So it's a general matrix multiplication for using this nice index notation in this Einstein summation convention. Right, so definition, and we already know this really, the trace of a matrix is the sum of the diagonal elements of the matrix. For example, we have A11, A12, A21, A22. So then the trace of A, we'll call this matrix A. Trace of A is A11 plus A22, which we could write as a summation. A, I. So that would represent the trace of a matrix. When you have something that has two indices and both of the indices have the same letter, it's basically the trace of that matrix. So the transpose, we already know a little bit about the transpose as well. Definition: the transpose of matrix A, which is maybe something like A11, A12, A21, A22, equal to, we'll call it Aij, is the matrix A transpose equal to Aj, which would be A11, A21, A12, A22. So basically, the elements here swap places. To get the transpose. So basically you reflect the matrix across its diagonal. To get the transpose of a matrix. So cool, good stuff. Now, this is going to be important. Remember I said a long time ago that the multivariable chain rule is the most important part. Well, what we're going to do is use our Einstein summation notation to write out the multivariable chain rule. So this is the partial derivative chain rule, multivariable chain rule revisited, multivariable chain rule revisited. And we're going to suppose xi, independent variable xi, is actually a function of other independent variables, u1, u2, um, for each I from 1 to n. Usually m and n will be the same number whenever we're talking about tensors, but in general it could be a different change of variables. We will just do, for now, we'll just do m and n are possibly different numbers. Then partial f partial uj be equal to the sum partial f partial xi partial xi partial uj. Right, we're summing over all the i's, and we could say for j equals 1 to m. So this is the multivariable chain rule written with our Einstein summation notation. Multivariable chain rule using summation notation. And we said for independent variables we always stick the index up. That's just a convention. There's nothing really behind that. It's just our independent variables, we stick the index up. All right, so this represents m partial derivatives, partial f, partial uj. And j can be any one of the values from 1 to m, so that represents m partial derivatives. So this one equation represents m partial derivatives. So this one equation represents m partial derivatives. Which is pretty powerful. It's kind of like the equation f equals ma. So similar to f equals ma. Well, in tensor notation, or our notation, we'd say fi equals mai. It's really three equations in one. So three equations in one. So kind of the same thing here. This multivariable chain rule using summation notation really is just like m equations in one equation. So that's going to be extremely important whenever we're talking about tensors later on. We'll have a single tensor equation. Well, that could represent who knows how many equations. It depends on what I and j or however many indices you have. So it just depends on what your indices can range over. So let's look at one more definition really quick. The definition is the definition of symmetry. This definition will be important for later on. So even though we're just kind of doing some more exposure to the notation, this definition does mean something to us. So definition, if a matrix A is equal to A transpose, then the matrix is called symmetric. So what would that mean? That would mean aij equals aji, or aij equals aji, or aij equals aji, just depending on whether you have indices up or down. So that's what we mean by a symmetric matrix. So that's the first part. The second part is if A transpose is equal to negative A, then A is called skew symmetric. So we call it skew symmetric. So that means aij would be negative aji, or aij is negative aji, or if they're both up, aij up equals negative aji up. So that's called skew symmetry. These two will be important for you to remember in the future. We'll come back and we'll show that certain tensors later are symmetric or skew symmetric. Well, we basically have to show that they satisfy these properties. Specifically in tensor, like in index notation, we'll show that these properties are true for certain tensors later. And then last definition. So last definition is that a matrix is orthogonal if A transpose is equal to A inverse. So that's a really special type of matrix. All right, so any questions? An example of an orthogonal matrix is a good one, easy one, is the identity matrix. Example, identity matrix is orthogonal because its transpose is just itself, and it is its own inverse, and therefore it is an orthogonal matrix. Let's see. There would another, let's see, maybe this one, 0, 1, 1, 0 times 0, 1, 1, 0 equal to 1, 0, 0, 1. So 0, 1, 1, 0 is also an orthogonal matrix. If you can think of this one as A and this one as A transpose. We're not going to go into a whole lot of linear algebra here, but orthogonal matrices are basically made up of columns of unit vectors of some form of basis. So I'm not going to go into great detail, but that's a more precise definition of what an orthogonal matrix is. Or, I mean, not more precise. It's an easier way to develop an orthogonal matrix, or to think about them. So, any questions? Next time we'll do like a little worksheet from chapter 2 stuff. I think what we'll do now is just we'll finish the live stream and hop over and get ready for our quiz. So, any questions, first of all, about the material? Maybe I do want to mention one more thing before we end. It goes back to like the beginning of the class for today, just kind of about the indices. If there are no questions, just kind of add one more thing about the indices and how to think about them. So know if we have one index, it's like a vector field, 3 components or n components. We'll call it like v1, v2, etc. If it has 2 indices, it's like what we call a matrix field, just a matrix of functions. So n by m components. v1, 1, v1, 2, v2, 1, v2, 2, etc. If it has 3 indices, it's like multiple matrix fields. So you could think of it as like a 3D matrix. So you could have like, say, v1, 1, 1, v1, 2, 1, v1, 3, 1, v2, 1, 1, v2, 2, 1, v2, 3, 1. And that just tells you that you're in the first matrix field, that last index on the bottom. Tells you this is the first matrix field. And then v1, 1, 2, v1, 2, 2, v1, 3, 2, v2, 1, 2, v2, 2, 2, v2, 3, 2. This tells you you're in the second matrix field. So 3 indices would basically be like a 3D matrix. So it's like a 3D array of functions. Okay. I don't know, does that make sense? Because we are going to see things with 3 indices and even 4 indices later on. So I want to make sure that the idea kind of makes sense, like what the indices would represent. It would represent like a 3D array of functions if you have 3 indices. The last index tells you which matrix you're looking at, basically. Is it the first matrix, the second matrix, or the third matrix? And you could basically like line all those up together, like here. You know, go back this way. So you could have like 3 matrices right here. So first matrix, second matrix, and then third matrix. Now, does that make sense? If you had 4 indices, that would be like having multiple 3D matrix blocks. 3D matrix blocks or arrays. So multiple 3D arrays. So then you could have, you know, let's say you have like A, I, J, K, L. Ij represents the place in the matrix, K represents which matrix, and L represents which block. So this would be like, let's say it's 2 by 2 by 2. This could be like L equals 1. And this would be K equals 1, K equals 2. And I can have a different block of matrices back here. And this would be something like L equals 2. And here, the first one would be K equals 2, or K equals 1, and K equals 2. So now it's just like multiple 3D blocks of matrices. That's what 4 indices would represent. So when we see something like this, Aij(KL) or Rij(KL), the first 2 indices tell you the row and column number. K tells you which part of the 3D part, and then L tells you which 3D block you're looking at. So I is the row, J is the column, K is which matrix, and L is which block. So I just want to, since we talked about that earlier, just want to kind of highlight that for, you know, other indices. You could have more indices. We're not going to go past 4, at least not with the real things that we talk about. We might do it just for fun and like, you know, for example problems, but in the real world, 4 indices is kind of the most that you see, specifically with something called the Riemann curvature tensor. So yeah, I guess that's where we'll stop for now. Switch over to Moodle and look at our quiz. So no questions, we'll wrap it up and see you guys in just a second. I'll send you a link.